All right, so the fun continues. We're going to look at De Moivre's theorem for solving equations. So lecture 35, specialist maths. If you're watching this video, hopefully you've seen the previous 5 videos on complex numbers. So intro to complex numbers, modulus, conjugate, and division, complex numbers in polar form, operations on complex numbers in polar form, and solutions to quadratics over the complex numbers. Something that will also be helpful for this video that's a bit unique is sequences and series, which we spoke about in lecture 3, particularly geometric series. So I'll put a link for that below, and we'll talk about that when we get to it. All right, what we'll do is talk about De Moivre's theorem for solving equations. So we'll look at some theory and some examples. Then we're going to look at roots of unity, which is a really fascinating idea, I think, and then properties of roots of unity. And then we'll look geometric sequences and the series generated by those roots of unity. This is what AI thinks De Moivre looks like. So, I don't know. I think it was a French dude. So this is what we're going with, apparently. I've got another picture of him here. So let's jump into it. We're going to look at, what he had to say about solving equations. So this theory part's a bit tricky, but I think it'll make sense with an example in a moment. So basically we can say we can solve equations of the form z to the n equals a, where a is a complex number, by using De Moivre's theorem. Now remember, you can get a bit lost here with all the different variables. Z is just a number. It just happens to be a complex number. So for example, this could be something like x cubed equals 8 in normal number land, but now we're dealing with complex numbers. So z to the n equals a. Okay, in order to solve something like this with complex numbers, you're going to express z in polar form, and a in polar form, I should say. So you're going to get z equals r cis theta. Okay, so we should know by now that a complex number can be expressed this way in polar form, where r is the modulus and theta is the argument. And then this is just another way we can represent a in polar form as well, just using different variables just to show that it's different. So Q cis phi, I think, is this Greek letter. So, of course, remembering cis theta is cos plus I sine theta. Cosine theta plus I sine theta. Okay, so then substitute all that business into the formula. So you're going to get r cis theta to the n equals Q cis phi. Okay, and then you're just going to compare. Well, firstly, I should say you're going to apply the power rule for complex numbers in polar form. So r cis theta to the n is the same thing as r to the n cis n theta. And we know that that's equal to q cis phi. So we just compare the arguments. So r to the n must equal q, and cis n theta must equal cis phi. So we can say that r equals the nth root of q just by solving for r. And n theta equals phi. But we have to add 2k pi because those angles begin to repeat. So remember, n theta is an angle somewhere around the unit circle, and if that's equal to some other thing phi, well, it would also be equal to phi plus 2k pi, because that would just be another full revolution around to get back to that point on your Argand diagram, shall we say. And the reason it's not plus or minus is because k is an integer, and integers can be negative. So you could also write phi plus or minus 2k pi, but since k incorporates negative numbers, that would also move in the negative direction as well. Okay, and then so just rearranging for theta, we get theta equals phi plus 2k pi on n, where k again is an integer. And all solutions to the equations can be found using this method. Now, it might be a little bit confusing. It's quite theory-based, but let's look at an example. Hopefully it will make some more sense. So if we got asked to solve something like z cubed equals 8 cis pi on 3. Okay, so what we want to do is just follow the steps from the previous part. So we can see that n is 3, q is 8, and phi is pi on 3. N is 3 from this here. Okay, so r cubed equals 8. So we're comparing the moduli, right? So, so we should be clear, just to be super clear, z is r cis theta, and the moduli of that is r. So r cubed is equal to 8. So r is equal to the cube root of 8, which is 2. And then step 2 says use the argument. So you're going to get 3 theta equals pi on 3 plus 2 pi k, because you're equating oh yeah, I should have put more working out here, but 3 theta is on the inside of r cis theta. So it's 3 on the left hand side, you've got 3 cis 3 theta. So 3 theta is equal to pi on 3 plus 2 pi k. And then you divide by 3. And then you get this. So these are your solutions for theta. And then to find your solutions, you just set k equal to 0, 1, and 2. So you just pick the first couple of integers. And I think visually this will help. So these are our solutions to this equation. Here is 2 cis pi on 9. Okay, and look, if we look, remember these circles represent a radius, and increasing a radius by 1, so radius of 1, 2, 3, 4, and so on. So this one here is at 2 cis pi on 9, it's on the second circle. This one here is at 2 cis 7 pi on 9. This one down here is at 2 cis 13 pi on 9. Okay, and so these are the solutions to the equation. Notice that they're all evenly spaced, and that's always going to be the case when you're solving these types of equations. They're all evenly spaced out around your Argand diagram. And you know, just to really drive it home, what it's saying is there's 3 solutions to this equation. So you could take this complex number here, if you multiply that by itself 3 times, because it's cubed, you will get this point up here, which is at 8 cis pi on 3. Okay, similarly, if you multiply this complex number by itself 3 times, you would get to this point also. And same deal here. You multiply this by itself 3 times, you'll get up to here as well. So sort of a visual diagram to show you what's going on there. Okay, hopefully that's making some sense. Let's look at the next thing where we have something on the right-hand side that's actually in Cartesian form. And hopefully you guessed. So here's another question. So z cubed equals 1 plus I root 3. Okay, again, z is r cis theta. Okay, note that 1 plus I root 3 equals 2 cis pi on 3. Okay, so obviously our first step here, given what we've just learned about the theory, is to convert this in Cartesian forms into polar form. And I'll leave that as an exercise for you to go back and have a look at the other video if you're not sure about how to do that. But I can guarantee you 1 plus I root 3 is 2 cis pi on 3 in polar form. And so we end up with this. And again, applying the power rule, we get r cubed cis 3 theta equals 2 cis pi on 3. R cubed equals 2, so r equals the cube root of 2. Okay, and 3 theta equals pi on 3 plus 2k pi. Okay, is an integer. Similarly, we get this sort of answer. So we get pi on 9 plus 2 pi k on 3 as our solutions for theta. Okay, here they are. So again, we're on, if we think about the moduli, it's the cube root of 2, which sort of gets us in between these two circles, because this circle here is a radius of 1. This circle here is a radius of 2, so we're sort of in between at the cube root of 2. And then this one here, again, we're just going to substitute values in for k until we start to repeat ourselves. Okay, so k is 0, we get the cube root of 2 cis pi on 9, so that's here. If k is 1, we get the cube root of 2 cis 7 pi on 9. And if k is 2, we get cube root of 2 cis 13 pi on 9, which is down here. Okay, all of these solutions are equally spaced by 2 pi on 3 radians around a circle of radius cube root 2, which is sort of the circle that would run around these points here. Okay, really to just drive this home again, if you multiply this by this complex number by itself 3 times, you'll get to this. Now this, I'm hoping you're guessing, is this, right? 1 plus I root 3 is that point there, is that complex number. Similarly, if we multiply this complex number by itself 3 times, we get over here, and if we multiply this by itself 3 times, we get over here. If you don't believe me, hopefully you do, but if you don't believe me, take this number and yeah, cube it and see what you get. You should get 2 cis pi on 3. Yep. All right, let the fun continue. So now is actually an interesting idea, something I find fascinating. Let's put that back to 0 for now. So let's talk about what's called the roots of unity. So the nth roots of unity are solutions to the equation z to the n equals 1. So previously we were looking at z to the n equaling a complex number. We looked at one that was in polar form, and we looked at one that was in Cartesian form. Now we're just looking at it equaling the number 1. And the solutions to this can be written in polar form as this, okay? So we get this business here. Essentially, if we just break it down, this is just cis, cos plus I sine of 2 pi k on n. And that should make sense. You just take your circle and you divide it by n. And so what you end up is this. So you end up with equally spaced points on the unit circle in the complex plane. So what you get is this. So this is, let me show you, when n is 1, so when n is 1, we get this point here, which is just the number 1. So z equals 1 because n is 1. So z to the 1 equals 1. That should make sense that that point is there. Okay, z squared equals 1. We end up with a point here and a point here. So you end up with 2 points. And you notice that they're equally spaced. And then, so there are squared roots of unity. And then we do our cube roots of unity. And we end up with a triangle, which I think is pretty nifty. And it's equally spaced. So we're always going to have one at 1. Then this one's going to be at 2 pi on 3, I believe. And then this one down here is at 4 pi on 3. 4 pi on 3 down here. Anyway, I encourage you to think about that. But anyway, we end up getting this situation, which I think is pretty neat. You end up getting what's called, they form the vertices of a regular n-gon centered at the origin. Okay. So yeah, we can just keep scaling that up, but we end up getting the vertices of a regular n-gon representing our roots of unity. And when we say roots of unity, we mean unit refers to the number 1. So z to the n equals 1. These are the solutions to z to the n equaling 1. So that's pretty nifty. And if we keep going, it sort of just goes like that. But you get the idea, hopefully. Some other properties just to be aware of. The product of all nth roots of unity is equal to -1 to the n minus 1. Come back to that idea in a little bit and have a think about that. But this is, I think, one's interesting. The sum of all nth roots of unity is 0, except for n equals 1. Okay, so n equals 1. Obviously, this does not we're not adding anything to it, so this is just the number 1. But if we look here, if we add these two together, if you think of them as vectors, this vector is pointing this way, this vector is pointing that way, so that equals 0. So when you sum up your nth roots of unity, you end up with 0, so which I think is pretty interesting. Okay, you're probably like, how does these numbers add up to 0? Well, let's look. This one here is obviously at the number 1. This one here is at 2 pi and 3. This one's at 4 pi and 3. But if you were to add these, this vector to this vector, think about it. You'd have a vector pointing here and a vector pointing there. If we add them together, you'd go like this, and then you'd be down over here. You'd be down here. So it'd be exactly -1. -1 plus 1 would give you 0. So it's pretty nifty. And then obviously these ones here, same deal, right? This vector and this vector cancel out. And similarly, this complex number and this complex number cancel out as well to 0. And they always cancel out. Again, the fifth root of unity might be like these don't cancel out, but they do. So again, if you think of this one plus this one, this vector plus this vector would give you 0. This vector, remember, you got to think of the direction as well. This vector plus this vector, if you add them together, you'd go like this. And it would be exactly the same size. It would be -1. How does that work? Oh, sorry, yeah. You go up here, and then if we add this part to it. Yeah, if you add this vector to this vector, you get to here. You must. Why is that not working in my head? All right, yeah, I don't know why I found that so hard to visualize. It is a bit tricky in some ways. So if you sort of think about it like this one and this one, the imaginary parts of these complex numbers will cancel out when you add them. So you'll end up with a real number that's about there somewhere, I reckon. And then here, when you add these, we add this vector and then you end up out over here somewhere. But the amount that you're past, the number 1, is the same as this part from the origin. So when you subtract them, you must get a vector that points here. So it's a little bit confusing, but then that vector, the resultant vector of adding this, and this is a vector that's here, or is the complex number that's there, and then you add that to that, and you get 0. Anyway, take my word for it that when you add all the complex roots of unity, you end up with 0 as the answer, which I think is fascinating. It's just pentagon's a bit hard to imagine. Maybe a hexagon's a little bit easier, but kind of cool nonetheless, I think. All right, let's just have a look at the last part. So what we'll talk about now is if we look at the cube roots of unity, for example, so let's put it to 3 because it's the cube roots. We can see that the first one is always 1, and then we get cis 2 pi on 3 and then cis 4 pi on 3. So what we can do is we can build up a bit of a sequence here. So more generally, for n greater than or equal to 2, the nth roots of unity are 1 cis 2 pi on n, cis 4 pi on n, all the way up to n minus 1, because when you get back to n again, you're back to where you started. So you do, you're going to be at 1. Oh, I should say you're at n. Let me think. We always start at 1, and then we go, you divide your radians, which is 2 pi, by the root of unity that you're interested in. So that gets you to a different second point, obviously. But you don't come all the way around, because then if you don't go all the way up to n, because that would take you all the way back to where you started, and then you just be repeating yourself. So you only go up to n minus 1. Anyway, this forms a geometric sequence with a common ratio of cis 2 pi on n. Because if you look at this, this is forming a sequence that goes 1, cis 2 pi on n, cis 4 pi on n. Now, it should be obvious to go from 1 to cis 2 pi on n, you're multiplying by cis 2 pi on n. But it's a little bit less obvious that to get from here to here, you're multiplying also by cis 2 pi on n. One way you can think about it is you divide this complex number by this complex number. And when you divide complex numbers, you subtract the arguments. So 4 pi on n minus 2 pi on n is 2 pi on n. So you can sort of see from here to here as well that the common ratio is what we're going to call omega, which is cis 2 pi on n. Okay, so we've just sort of called this common ratio, we've sort of called each term in the sequence, we've called the ratio omega, but then you can also see that omega can just give us each term in the sequence, because it goes 1, then it goes omega, then it goes omega squared, then it goes all the way up to omega to the power of n minus 1. Again, we don't go all the way to n. We only go to the second line. We go to the end of our root of unity. So for example, we go to here. We go all the way around to 10 in this case if we're talking about the 11th roots of unity, or we go up to 14 if we're talking about the 15th roots of unity. In any case, this is why we looked at geometric series earlier on, because when you add all this together, 1 plus omega squared all the way up to omega to the n minus 1 is omega to the n minus 1 over omega minus 1, which equals 0. Okay, so which is what we said before, when we said before that the sum of the nth roots of unity equals 0. This is the reason why. And you're probably like, why on earth does this equal 0? We know that omega to the n is equal to 1. And you're like, what does that mean? Well, let's look. Omega to the n is when you take this, cis 2 pi on n, and raise it to the power of n. Remember, you apply the power rule of complex numbers, so it becomes, there's a coefficient of 1 here, 1 to the n, that is just 1. Cis 2 pi on n times n, which is just 2 pi. Cis of 2 pi is 1. So omega to the n is just equal to 1. So this here, omega to the n minus 1, well, that numerator is 0, and 0 divided by anything is 0. You're probably wondering why this series is equal to this expression, and I'll put a link below talking about geometric series. But once you know the common ratio, you can work out what the series evaluates to. And in this case, it's 0. And that's just a proof of the fact that when we add all of our roots of unity, we always get 0. So let's leave it on a decagon, because why not? Dodecagon even, because that's a nice shape. It's all quite beautiful, isn't it? Anyway, if you found this video useful and you're following along with this series, give us a thumbs up. Let us know how you're going. Feel free to reach out, ask any questions. Good luck with everything you're doing, and I'll talk to you soon.